Okay, let's get started. Any questions on what we're doing? Any questions?
Maybe the second one.
Second problem. What is it?
Yeah, I think it's
16. So, x is x over square root of x squared plus 1. And what's the question? It doesn't say the question here.
Prove the following inflection point squared with 1 and the maximum.
Oh, okay.
And where it's-
On the whole line, or?
And where it's concave up and concave down.
Where it's concave up and concave down. Okay. Okay. So, did anyone? So let's just take some derivatives here. Right. So maybe let's write for convenience. Let me write this x squared plus 1 to the negative 1/2. Okay. So let's take the derivative. Take the first guy times the derivative of the second guy. Negative 1/2 x squared plus 1 to the negative 3/2 times 2x, right? Plus the derivative of the first guy times the second guy. So that's going to say that. Okay. So you end up with what? The 2's cancel off. You end up with negative x squared over x squared plus 1 to the 3/2 plus 1 over x squared plus 1 to the 1/2. Right? Okay. So what you want to find out where this is equal to 0? Where? How do you do that? Yeah. What?
Sorry, I don't want to interrupt.
Yeah.
Can you go back to just that derivative where you, yeah.
Yeah. Okay. So we're going to use the product rule on this, right?
Yeah.
So you say the first guy times the derivative of the second guy. How do you differentiate this? Well, it's going to use the chain rule, right?
Mm-hmm.
So you take the derivative of the outside thing, which is x to the something to the negative 1/2. So it's going to be 1/2 that's something to the negative 3/2, right? By the power rule.
Okay.
And then, so it's going to be negative 1/2 that thing to the negative 3/2 times the derivative of the inside guy.
Okay.
Well, the derivative of the inside guy is 2x.
Okay.
So it's just the product rule combined with the chain rule. Right? And then, so that's the first times the derivative of the second. Then the derivative of the first, which is 1, times the second, which is that.
Oh, okay. Thank you. That makes sense.
Okay. And then, right from here, what do you do? Anybody? You want to find where this is equal to 0, right? So
common denominator.
find common denominator, right? So let's multiply this guy, say, by x squared plus 1, right? We'll multiply the second guy by x squared plus 1 to the 2/2, right? X squared plus 1 to the 2/2. Right? And then you end up with negative x squared plus 1 over x squared plus 1 to the 3/2. So where is it 0?
It's at 1.
It's 0 at 1 and
No, just at 1.
just at 1. So you want for this thing to be 0, you need the numerator to be 0, right? So 1 minus x squared is 0. In other words, x squared is 1. In other words, x is plus or minus 1. Right? X is plus or minus 1. Okay. Right. And so what do you see? That this guy, this thing, the derivative is 0 at these 2 points, right? And you see that this number on the bottom here, what can anyone make some observation about this? X squared plus 1. Yeah. Okay. It's always positive, right? It's always x squared plus 1. You always get a positive number, and you're taking the the square root of the cube of that, right? So you get this positive number on the bottom, and you have 1 minus x squared on the top, right? This downwards parabola. So you're taking a downwards parabola and multiplying by something always positive, right? So Mercedes.
Sorry, what did the numerator just be 1? Yeah, I'm not.
Did I make a mistake?
X squared.
Oh, I'm sorry. Thank you. Sorry, I did make a mistake. Sorry. Okay. Sorry. So we get negative x squared plus x squared plus 1. Thank you. Okay. So you get over x squared plus 1. Yes. Great. Even better. So you get 1 over x squared plus 1 to 3 halves. Okay. Right? Thank you, Mercedes. You saved us. Okay. So what do you say about this?
You can't be 0.
It's never going to be 0, right? This is never going to be 0, right? So this in fact this is always positive. So your function is positive everywhere, right? And so that tells you that your derivative is positive everywhere. That tells you that your original function is always increasing. Right, so f is increasing everywhere. Okay. And that makes things simpler. Okay. So let's take the second derivative. Okay. And you get so this is x squared plus 1 to the negative 3 halves. We differentiate it. Oops. Take the second derivative. Right? You get negative 3 halves x squared plus 1 to the negative 5 halves times 2x. Right. Okay. So what do you say about that? Well, that gives you x over, well, negative 3x over x squared plus 1 to the 5 halves. Okay. So, again, this thing on the bottom is always going to be positive, right? And so, what do you say about the second derivative? What do you see about the second derivative? Yeah, its inflection point is 0, right? So at 0, you see that the second derivative is 0, and before that, the second derivative is positive, right? And after that, the second derivative is negative. Okay. Oh, yeah, go ahead.
Can you explain again why you singled out the denominator for that derivative? The denominator from the one before?
What do you mean by singled out the denominator?
Like where you got this x squared plus 1 to the negative 3 halves.
This, okay, that's this.
Right.
That's
Why
this.
did you then turn it into?
We want to take the second derivative of it, right? So that was our first, we figured out the first
Oh,
derivative
that's still the
already.
first derivative.
And now we're getting the second derivative. So the first derivative was positive everywhere. Now we're looking at the second derivative. It's positive here, negative here.
Okay.
Yeah, Stefan.
There's a change in signs on the left and right side of the inflection point
Yeah.
for the second derivative.
Yeah.
Is there no maximum minimum because it's like a concave up and a concave down?
Well,
Or
actually,
concave
so from over here, is there a maximum or minimum?
Yeah, we can already tell from that.
Exactly. Yeah, we can already tell.
But is it also true for the like if there's a change in cavity? Is that a point? Like is that an inflection point where there wouldn't be a maximum? Wait, never mind. I actually felt like confused overall on how to use the second derivative.
Second derivative. So you use the second derivative test when you have a critical point already.
Okay.
Okay, it's not like I say, oh, it's concave up here, I've got minimums here, or something like that, right? You have to have, first you have to have a critical
Yeah.
point to apply it to.
Okay.
Okay, so don't be reckless
Okay.
about what the second derivative tells you.
Okay.
Okay, first you have to have a critical point. We don't have any critical points here.
Yeah.
So.
Okay. And if you do, you have to look for where those critical points are in the second derivative test. And
Yeah, so
then
if-
offer concavity and
Right.
it's-
If we had a critical point here, then we'd say, oh, look at that critical point, the second derivative is positive, so we're at a min.
Okay. Okay. Awesome. Thank you.
Sure. Okay. Yeah, Claire. Whoever you are.
I have a question about just how did you simplify the negative x squared plus 1?
This here.
The one below.
Here.
Yeah.
Yeah.
Well, the negative x squared plus the x squared becomes 0, and we're left with 1 on the top. I'm not sure.
Oh, I see. Yeah, got it. Yeah,
Okay.
sorry, I was looking past that.
Okay, that's all right. Okay, everyone all right? So what was the hard part? It seems like this was one that people had some trouble with. What was the
The
hard part?
actual like derivatives.
Taking derivatives.
Yeah.
Taking derivatives.
Also, the
It's just very
instructions,
confusing.
the instructions
Yeah,
didn't say that
like,
no critical points were an option, so it's possible.
I'm fine agreeing.
Like, because in
They
the
didn't,
last,
they didn't say it was possible, so you
well, in
could-
the last one, they were like, sometimes there will be no answer in the instruction, but this time they didn't say that. So, I thought we were doing something wrong.
Okay, but trust yourself, right?
I don't trust myself.
You don't trust yourself. Even if even if you don't have faith in yourself, just trust you. Just charge your head blindly. That's okay. Okay.
Advice from my math teacher.
That's right. Just charge your head blindly and hope it works out. Okay. So you reach this point and say, oh look, there seems to be no critical points. Okay, no critical points. No critical points.
Or start over until you get critical points.
No.
There's no critical points.
No. Just make your mistakes and go on with them. Okay. So,
Just go on.
yeah. Don't ask me about how my life has turned out. Okay. So right, you have to be able make sure that you understand the basic rules of differentiation, right? The only thing that we're doing here, product rule, chain rule. That's it.
Yeah, it's one of like the
Product rule, chain rule, arithmetic. This the hard part?
It's one of the fractional degrees, like it's
See, that's
I
the
still don't
trouble.
understand.
That's the trouble. Yeah, there's something. This is more fundamental stuff, right? Right, you're looking for a common denominator, right? Common denominator would be x squared plus 1 to the 3 halves, right? So you multiply both sides by x squared plus 1 to the 2 halves. That's x squared plus 1 to the 1, right? Over itself. Okay. Yeah, there's some. Yeah. I'd like to sort of overhaul the entire, pre-college math teaching,
Yeah.
so that everybody feels a bit more secure about their basic skills. Anyway, so okay, so today we're going to be doing L'Hopital's rule.
Was that 4.7?
This is 4.7. Yeah.
Yeah,
So
4.7.
we're skipping 4.6, which is just graphing, which I don't think is a useful skill at this point in history. Okay. So you have all the information, right? You can figure out everything you need to create a graph if you want to at this point, right? You can figure out where you have a max, you have a min, where the function's increasing, where the function's decreasing, where the function's concave up, where it's concave down. Okay, that's enough for me. I don't really see the point in making you learn the sort of archaic skill, the obsolete skill of drawing graphs. So today we're going to do L'Hopital's rule, which you can think of as the rule about competing infinities. Okay. And the historical comment is that this rule was actually discovered by one of the Bernoullis, one of the Bernoulli family. It's really called Bernoulli's rule. But apparently L'Hopital was the sponsor of something, like was Bernoulli's sponsor. So he put his name on it, or was allowed to put his name on it. Okay, so here's the idea. You have something like this. The limit of a quotient as x approaches something. And this c could be, some finite number. It could be infinity. It could be negative infinity. It could be some number from the left-hand side or some number on the right-hand side. Anyway, you're considering something like this, but individually, each of those things goes to 0. Okay? If you took the limit of f as x goes to c, you got 0. So you considering this when each of those things goes independently to 0. Even so, the limit might still exist. So for example, if I say, suppose I look at x squared over x squared as x goes to 0, right? Which is x over x, to make it even clearer, right? The top goes to 0, the bottom goes to 0, but does this limit exist? Sure. What's the limit? 1, right? The limit is 1, because this guy is 1 everywhere. It's not defined in 0, but it's 1 everywhere else, right? So this limit is 1. Okay. So the limit might well exist, right? Or it might not exist, right? Or maybe a more sophisticated example is one that you've seen before, right? The limit of sine x over x, right? We saw that actually equaled 1, even though sine x goes to 0, and x also goes to 0 as x goes to 0. Yeah. Go ahead.
But those are like continuous functions.
Those are continuous functions, yeah.
So, but you can't plug in 0.
You can't plug in 0 because there's no, it's not clear what it means there. Yeah. Right. What does it mean to have 0? If you plug in 0, you get 0 over 0.
Yeah.
Are you saying that 0 over 0 is
0.
0?
Is it?
It looks like it should be 1, right? But if I look at this, what if I look at this? This also becomes, if I plug it in, it's 0 over 0. But what's the limit here?
0.
The limit here is 0, right? Right? Because, right, away from 0, x squared over x is just x,
Oh, yeah.
right? So this limit is the limit of x as x goes to 0. So that's 0, right? Or, if I look at this, right, that's also 0 over 0, but what's the limit? Let's say from the right-hand side.
I feel like 1 over x.
1 over x, as x approaches 0 from the right-hand side, is going to be
Just the end of
1 over x, 1 over x, 1 over x, infinity,
Oh, yeah.
infinity, right? Or if we went from the left-hand side, negative infinity. Okay. But if you plug these in, right, if you plug in the value, right, you get 0, it's all 0 over 0, right? Right, so just to say that plugging in for 0 and getting a 0 over 0, it's not really clear what you mean. Okay, that is, it could be a lot of different answers. Okay. So really, the way you want to think of this is, Suppose we did these things independently. Okay, here's the way to think about it. Suppose we did these things independently. Like, as x goes to 0, we let the top go to 0 first. Okay, then we would get 0 over x, and then we let the bottom go to 0. What would the limit be then? Let the top go to 0 first. Do you understand what I'm saying? If I say, I'm looking at the limit of x over x, say as x goes to 0, okay, and I let the top go to 0 first, right? Then I get 0 over x, right? That's to say 0, right? And then if I let the bottom go to x, then it just stays at 0 the whole time, okay? But if I let the bottom go to x first, then what happens?
Let the bottom go
I'm sorry, let the bottom go to 0 first. So I have something on the top. Suppose I have something positive on the top. And let the bottom go to 0 first.
It's gotta be undefined? Is that-
Well, it'll go not undefined, but I have something on the top. Suppose I have like some number. I'll do this one. I have two numbers, x and y. Okay. And y is bigger than 0. If the x goes to 0 first, then this thing heads off towards infinity, right? Because you're dividing by something smaller and smaller, this thing heads off towards infinity, right? But if I let the top go to 0 first, then this thing goes to 0, right? So you want to think of this as sort of a competition, Here, both guys are heading towards 0 at the same rate, and you end up with 1. Okay. Here, the top guy is going to 0 faster, right? The top thing, x squared, is going to 0 faster than x, right? If you look at the graph, right, as we go in, the x squared actually zooms down to 0 faster, right? And you end up with 0. Here, the x squared is going to 0 faster, and so the x squared wins out, and you end up with infinity. Okay. So really, this 0 over 0 stuff is sort of a competition between infinities, or a competition between heading towards 0. How fast you head towards 0. Okay. Right. So does that make sense? Is that making any sense to you?
Can you repeat what you said about the y axis?
Let me not do it concretely, and I'm just going to do it abstractly. Okay. You have two functions. Okay. And suppose, again, you know that, say that the limit of f of x as x goes to c is 0, the limit of g of x as x goes to c is also 0. Okay. So, competition. Okay. Okay. So you're looking at the limit of this ratio, right? What would happen if I let the f of x go first? I say you get to go first, f of x. You get to do it. You get to take your limit first. Okay. Then what would happen? Well, the f of x would go to 0, right? F of x would go to 0, and then we'd end up with 0. Right? Okay. Suppose I said g of x, you get to go first. Okay. If g of x got to go first, well, then g of x would go to 0, and then we'd end up with some sort of some infinity, maybe, right? As long as f of x was not 0, right? Then we'd head off towards infinity, right? Okay. But it turns out that so what we're interested in is both of these heading towards 0 at the same time, okay? And what will happen is that they'll sort of balance out, okay, depending on how fast they go. So let me put up the statement. So here's L'Hopital's rule. L'Hopital's rule says this: if blah 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 blah. Okay, if a bunch of things, okay, I'm going to leave that blank for a second, then the limit of f of x over g of x as x approaches c turns out to be the same thing as the limit of f prime x over g prime x as x goes to c. So now put in the hypotheses. If f and g are differentiable on, say, some interval excluding a point c, where c is in the interval. So you have some interval ab, and you have some point C. And these functions are differentiable on the interval, but maybe not at that point C. And the limit of f of x as x approaches C is 0. The limit of g of x as x approaches C is also 0. Then the limit of the quotient actually turns out to be the limit of the quotient of the derivatives. Let me do some examples to make it clear what we mean by this. So if somebody gave you this one, sine x over x. Okay. Sine x over x, this is one we did it already, but suppose we forgot it, and now we remember L'Hopital's rule. Okay. L'Hopital's rule says this limit is going to be the same thing as the limit of the derivative of the sine, that's cosine, over the derivative of x. Well, the derivative of x is 1. Okay. And so what do you get? The limit of cosine as x goes to 0. What's that? 1, right? You get 1.
So you don't, sorry.
Yeah.
So you don't need to apply quotient rule.
We're not taking the derivative of the quotient, but we're taking the derivative of the top and the derivative of the bottom. So it doesn't say that the limit of the quotient is the limit of the derivative of the quotient, but rather the limit of the quotient of the derivatives.
That's what I wanted you to say.
Yeah. Does that make
That
it
makes
clear?
sense, yeah.
Right? This is the limit of the quotient equals the limit of quotient of derivatives. Right. Or here's one that I think you saw in your homework around the same time. The limit of sine 3x over sine 2x as x approaches 0. Okay, take 20 seconds and figure it out. Use L'Hopital's rule. It's going to be the limit of the quotient of the derivatives. Well, what's that? Okay, turn to somebody next to you and say, the answer is?
Oh, I don't know.
Okay, would anybody like to talk about it? What's the answer? Yes. Yes, it's 3 halves. Very good. So what did you get? What's the derivative of the top and bottom?
I was changing, so it's 3 over 2.
Right. And so you get 3 halves, 1 on the top and bottom. Right. So you get 3 halves. Yeah, Mariah.
Wait, I feel like, so it can't be differentiable at C, right?
It need not be. It doesn't have to be.
Oh, but it can.
It could be. Yeah.
Okay.
Yeah. It's just that we don't need it to be there. Okay. Okay. Let's do another one. Say the limit of the natural log x over, say, x to the 0.000, no, x to the what? Oh, I'm sorry. This is not the problem. X goes to infinity. Sorry. Yeah. Right, because it's not in the right form. Okay. So actually, let me fix up. Sorry. Before we do that problem, let me add a little bit more here, okay, to the description of the theorem. So so this thing here saying or the limit of f of x as x approaches c is plus or minus infinity, and the limit of g of x as x approaches c is plus or minus infinity.
If f of x is, if f of x's limit is approaching positive infinity, does that mean g of x also has to be approaching?
No, it could be negative. These are
It could be
separate.
opposite.
Yeah, it could be opposite, it could be the same. Okay. 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 So I think here it's the idea of a competition is maybe clearer, right? The top guy, as x goes to infinity, what does natural log x do? What does natural log do as x goes to infinity?
2 times 7.
What also?
I was going to say e. Wait, no.
Natural log x, right? Here's natural log x. As x goes to infinity, what happens to natural log x? It also goes to infinity, right? What about x to the 1/2? As x goes to infinity, you might?
It
Also goes to infinity. So you have two things that are going to infinity, right? If the guy at the top goes faster to infinity, then this is going to head towards something huge, right? If the guy on the bottom is going faster, then what's going to happen? It's going to go to 0, or maybe it'll balance out at some number. Well, let's see what happens. Okay. So, so let's use L'Hopital's rule, and what happens? You get the limit as x goes to infinity of what? Well, it's the derivative of the natural log. 1 over x, right? And you divide that by
1/2 x to the negative 1.
1/2 x to the negative 1/2. So 1/2 x to the negative 1/2. Let me write it like this. 1/2 x to the negative 1/2. Okay. So you have 1 over x. I'm gonna bring that down. Right? I get 1 over 1/2 x to the negative 1/2 plus 1. Right? I have x to the negative 1 on the top. I'm going to bring that down. Right? X to the negative 1 on the top. I bring that down. Right? And so you end up with 2 over x to the 1/2.
Can you explain that last time?
1 over 1/2 is 2, right? And x to the negative 1/2 plus 1, well, negative 1/2 plus 1 is 1/2.
Oh, the 1 is in the exponent.
Yes,
Is that okay?
1 is the exponent.
And that's it? That's the line?
We haven't computed the limit yet. We've just simplified, right? So as x goes to infinity, what happens? The whole limit goes to 0. Right. The whole limit goes to 0. And so that tells you that x to the 1/2, hold on, I'll hold on a second. Okay, so that tells you that the x to the 1/2 beats the natural log x, right? X to the 1/2, right? We're looking at this race between natural log x and x to the 1/2. We get 0, right? So x to the 1/2 beat out natural log x, right? It went to infinity faster than natural log x. What if I had natural log x over x to the 0.1, say? What's going to happen there Well, I'm going to get, again, the derivative of natural log x is x to the negative 1. Right? The derivative of this guy is going to be 0.1 x to the 0.1 minus 1. Right? Right? By the power rule. Right? And what happens? What do I get in the end? The limit as x goes to infinity of, again, I bring this guy down, or I could say it this way, I cancel off the negative ones, right? And I end up with 1 over 0.1 x to the 0.1. Right? So as x goes to infinity, what do we get? 0. Okay. Who sees what I'm going to say next? Can anyone see what I'm going to say next? What if I take x to the 0.01? Well, again, you're going to get the limit by L'Hopital's rule. We're going to get the limit of x to the minus 1 over 0.01 x to the 0.01 minus 1. And what happens? Can anyone see?
It still goes to 0.
You're going to get 0 again, right? Because you get the limit of 1 over 0.01 x to the 0.01 as x goes to infinity. That's 0 again. Okay. What does this say about the natural log? The natural log loses to everybody, right? The natural log, if I take x to the 0.01, what if I take x to the 0.00000000000000000000000 sorry, 01. Sorry, this is what I do with my daughter. I say, Dad loves you very, 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 very. And she gets frustrated and says, much, 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 much. Sorry. Okay. In any case, yeah, she doesn't say that. She doesn't play along anymore, but she did when she was 2 or 3. Now she's 7. She doesn't play along. Okay. So you get 0, right? So no matter how small the exponent here, right? No matter how small the exponent here, natural log loses, right? That's sort of a natural log is slow, right? That's how you think of this. Natural log is slow. Yeah, Mariah.
Okay, but if you write it like, I don't know, I was writing it like 1 over x over 0.1x, so like, 0.1 minus 1. Wouldn't the 1 over x go to 0 faster? Wait, doesn't it mean?
The 1 over x goes to 0,
Yeah.
right? That only well, I mean you can't really separate it, right? Because you've got this 1 over x, right, and you've got this 0.1 x to the right. So you have something negative. You also have something down here, right? So what is this? This is 0.1 over x to the 0.99. Right. Right. So you have to, I mean, you can't take them separately. This is the same. This thing here that you're talking about is the same thing as this, right? So it goes to 0. Wait. So what do you say it again, Maria? I'm not following you.
I mean, I guess so. If you have what you wrote before, like 1 over x over 1 over like 0.1 x to the 0.9, was it?
How about let's look at this one? This one's maybe
Yeah.
easier to see.
Sure.
Okay. So we're over here, and we have 1 over x on the top, and we have 1 over 2 square roots of x on the bottom. As x goes to infinity.
So doesn't the 1 over x get to 0 faster?
That's good. Then we get 0.
Yeah, so wait, natural log wins.
Natural log loses, right?
It's faster, isn't it?
No. Look, if we take the limit, we get 0. So the guy on the bottom is the winner.
Okay, so the winner is the one that like is still in the game, like it's not at 0. I was confused. Okay, I guess I was confused about winning and losing. I thought like it's a race to 0.
Think like this. If as x goes to infinity, natural log x goes to infinity,
Okay.
right? As x goes to infinity, x to the 1/2 goes to infinity, right? Who goes faster? If the guy on top goes faster, then we'll end up with infinity. If the guy on the bottom goes faster, we'll end up with something that's not infinite, maybe 0.
Okay.
Okay. In this case, the guy on the bottom goes a lot faster, and we end up with 0.
Okay.
Even though the top's going to infinity, the bottom is increasing even faster than that.
Okay.
Okay, so that's the idea of the race here. Okay, and what we're seeing here is that if you take natural log against any power, then it loses. Okay. How about if I take the limit, so here's another one, limit of x squared over e of the x as x goes to infinity. Let's just talk about this first a little bit, okay? So what happens to x squared as x goes to infinity? What goes to infinity? What happens to e to the x as x goes to infinity? It also goes to infinity. Okay. Who do you think is going to win? Who votes for x squared? Who votes for e to the x? Okay. So let's see what happens. We use L'Hopital's rule. We get 2x over e to the x, right? Because e to the x doesn't change, right? So L'Hopital's rule. I usually put an h in a circle to indicate that I've used L'Hopital's rule. Okay. Okay. Did that help us? We still get infinity over infinity. Okay. But L'Hopital's rule says we can use L'Hopital's rule again, right? Because right? Because we get infinity over infinity. So let's do it again. Right? We differentiate again. We get 2 over e to the x as x goes to infinity. Well, what's that? 2 over e to the x. That's 0. Okay. So e to the x won. Right? E to the x was the winner. Right? E to the x goes to infinity faster. Now maybe you know what I'm going to say. What am I going to say? E to the x always wins. Yeah. Suppose I take 1, 0, 0, 0. Just I take x to the 1,000.
What if it's 1,000 to the x?
That's something different.
Oh, okay.
That's something different. So yeah. So e to the x beats any polynomial. Is what you want to say here. Okay. So what's going to happen here when we differentiate?
Like 0, 0, 0, 0, 0, whatever, x over e to the x, and then we differentiate again.
So we're going to get 1,000 x to 999 over e to the x. X goes to infinity. So again, we get infinity over infinity. So we differentiate again. We differentiate again, we differentiate again. We keep on going until what happens in the end?
It's just the number and no.
You get 1,000 factorial on the top, right? And e to the x on the bottom. Right? You get 1,000 factorial on the top. It's just some number though. Right? E to the x on the bottom, as x goes to infinity, you get 0. Okay. So what you're saying here is e to the x is fast. Right? Or faster than any polynomial. Faster than any polynomial. So, yeah.
But then when you say ln natural log x is slow and loses to everyone, are you then saying it loses to any polynomial?
Well, it loses to actually slower than any power of x. Yeah, maybe it's better than, I should say, it's make more symmetric to say than any power of x.
Okay.
I should say positive power of x.
So if e to the x was on the numerator, then the answer would be infinity.
Yeah,
If natural
yeah.
log is on the denominator.
If natural log is in the denominator, then we get infinity.
Okay. Yeah. Okay.
Yeah, we get infinity. Okay. Okay, so I hope this is giving you some sense of L'Hopital's rule. So L'Hopital's rule is like how you decide who wins this competition, right? You've got two things; they're both heading off to infinity, but in fact, sometimes one of them is a bigger infinity, right? Goes to infinity faster than the other, right? Or two things are heading off towards zero. Well, which one gets to zero faster? And L'Hopital's rule helps you decide the winner. Okay, next time we'll do some more with L'Hopital's rule.